Welcome to a code report solution video. My name is Connor, and in today's video, we're going to be looking at a single problem and solving it in 4 different languages: APL, BQN, which are both array languages, and then C++, and then CUDA C++. This video is sort of inspired or a response to a video that was done by an individual by the name of Asher Mancinelli, who solved it in BQN and then went to solve it in C++, specifically CUDA C++. And at some point in the video, Asher mentioned, if you have alternative solutions, I'd be curious to know what they are. So I figured I'd make a video sort of responding to it and solving it the way that I would. So without further ado, let's take a look at the problem that he solved in that video, which is called first missing positive. The problem states, given an unsorted integer array nums, return the smallest missing positive integer. And the problem goes on to state you must implement an algorithm that runs in O(n) time and uses constant extra space. I believe Asher sort of ignored these, so I'm going to ignore these requirements as well. But if people are interested, maybe I will make a follow-up video where we actually take these criteria into account. And note that this problem becomes a lot easier if you ignore these. And so Asher, in his solution, uses a sort primitive. And so that's what we're going to do in our solution as well. So let's take a look at a couple examples. Here are the 3 examples that LeetCode provides us with. The first one is 1, 2, 0, and the answer is 3. The second example is 3, 4, -1, and 1, and the answer is 2. And the third example is the numbers 7, 8, 9, 11, and 12, and the answer is 1. So the way to visualize this, or at least how I visualize it, is if you can think of the positive numbers starting from 1 and increasing, you basically want to identify the ones that already exist in your list. And then once you've done that, you just basically pull out the first one that doesn't exist in your list. So for our first example, we're given the numbers 1, 2, and 0. So we have 1, 2, and the first missing one is 3. For the second example, we do the same thing. 1, 3, and 4 exist. That leaves 2 for our answer. And for the last one, we don't have any of these sort of early numbers, so it's just going to be 1. So here you can see 3, 2, and 1 correspond to the answers. And this is basically how we're going to solve this problem. One of the sort of tricks that you need to note is that we know our answer is going to be one of the values that exists between 1 and the length of our list plus 1. So if we were to remove basically the 0 from our first example and we just had the numbers 1 and 2, we know our answer is 3 because in the worst case, the largest possible number that we're going to get is going to be in the case where we have basically a permutation of the numbers from 1 to n, where n is the length of our list. And then the first missing positive is just going to be n plus 1. So if we basically can figure out just which of the numbers have we not chosen in between 1 and n plus 1 and just choose the first of those, that'll be our answer. And that's how we're going to solve it in APL. So this is our solution in APL, which is a bit overwhelming. And I'm not going to try to explain this just by looking at this code. We're going to hop over into our APL ride editor and build this solution up incrementally, which will make it, in my opinion, I think way easier to understand. So let's do that now. So here we are in our ride APL editor. I will leave a link in the description down below for those of you that want to check it out. And we're going to solve this first in APL. So I've taken our second example, the 3, 4, -1, and 1, and added one more negative number and a number outside of the range of our length of our list, which here I believe is 6. And that value is going to be 10. So as I mentioned sort of in the description of how to solve this, the first thing we want to do is to remove all the negative numbers. Or that was sort of implicit in my description that we only care about numbers that exist between sort of 1 and the length of our list. So the first thing we're going to do is remove the negative numbers. So how are we going to do this? We're going to make use of an algorithm called either replicate or compress, which when placed inside a fork, a 3 train, where the left argument to compress, so this is compress here, the left argument is a Boolean mask. Here, if we just hand write it out, it's going to be 1, 1, 0, 1, 0, 1, which corresponds, all the ones correspond to the positive numbers. And then, so that's our left argument. And on our right argument, we want our list that we want to filter. So in this case, we just pass it the identity function. This is basically going to remove any of the elements that correspond to zeros in our Boolean mask. So here we're left with 3, 1, and 10, which is exactly what we want. So the question is, how do we generate our Boolean mask, which corresponds to all of the positive numbers? That's pretty straightforward. We are just basically going to do 0 is greater than, or sort of less than in this case, but we have it flipped. So we're checking here, are all of our elements greater than 0? And because this is an array language, we can do this operation with a scalar and a vector, and it works. So this is going to give us our Boolean mask. So pretty fantastic. We just copy this. paste it, and ideally, in an ideal world, like a BQN world, which we will get to later, this would work. However, it does not. It actually wouldn't work in BQN because we need to fix the first issue. So what's the first issue? It's that this fork or 3 train is expecting 3 functions, but here we have 3 functions plus an array. So we need to bind this 0. So currently, this less than operation is a binary operation, but if we bind the 0 to it, it turns it into a unary operation. So now we have 3 functions, a unary operation, and a binary operation. However, it's still going to work, not going to work, because in APL, it doesn't know how to disambiguate between a reduction here or the compress verb. So in order to do that, we have to unfortunately add these 2 glyphs to remove the ambiguousness. And if we do this, then we get what we are after. In BQN, you'll see that you don't actually need to do this, which is really nice because it's one of my least favorite parts of Dialog APL. So once we have this, now we want to basically sort these elements. And unfortunately, there's no sort primitive in APL. You just basically have to memorize that it's enclose, atop, grade, index, identity. And so this seems a bit noisy, and that's because it is, but if you program in APL enough, you'll just learn to memorize this as sort of the incantation for sorting. And sure enough, if we do this, we now have our sorted list of positive numbers. And now what we want to do is basically we want to pad zeros at the end of this list to get back to our original length of our list so that we can compare this to the sequence, the iota sequence 1 to the length of our list, which is going to be 6 in this case. So in order to do that, we can basically use a verb or function called take. And take basically takes the first n elements. And so if we do 2 take on 1, 3, 4, 10, we're just going to get back 1 and 3. If we do a 4 take, we just get our whole list. And if we do a 6 take, it's going to pad it with the default value for whichever type that you have. And because we're using integers, that default value is 0. So here we're going to get 2 extra zeros, which is fantastic. So now all we need to do is figure out a way to not hard code this 6 here. And we can do that by basically turning this whole thing into a bigger fork. So if we compose these 2 unary functions, our sort and then our 3 train for filtering out all the negative numbers, this becomes another unary function. So this will be the binary function in the midst of a fork. And we need to put this all in parentheses. And then we basically need to figure out how to get 6 here. And we actually don't even want 6. We want 7. In the case that we do end up with 1, 2, 3, 4, 5, 6, we want to have that 7 there to choose. So it's actually the length of our list plus 1. And so we can get the length of our list by just doing tally, if I can type it correctly, which is going to get us back. And if we want to get the length of our list plus 1, we just need to do a 1 plus, and then we need to put this in parentheses so that it parses correctly. So this is going to be another 3 train. So it's basically, we've got a 3 train, aka a fork, where the sort of top level binary function is take. And then on the left, we have another 3 train. And on the right, we have sort composed with another 3 train. And if we do all this, we should get our 1, 3, 4, 10, 0, 0, 0. So we're making pretty good progress here. And the next thing we want to do is basically put this right next to and then compare with. So I'm just going to hand code this again. The sequence, sorry, that should be a 5. The sequence should be iota 7. So put this in parentheses. And if you can see here now, if we basically put these side by side and then compare what's the first pair of elements where these 2 aren't equal to each other, we can identify what our first missing positive is. So how are we going to do this? First, let's start by just generating our iota 7. So we can do that by doing iota tally. And for now, I think we can leave off the parentheses. And so now this is going to be the left function of our 3 train or our fork here. So we need to compose this. That'll get us done here. And then basically what we want to do is we want to compare which of these are not equal, which I believe is 8, to our original list. So once again, we have another 3 train here. You can see by building up this expression how important the S prime combinator is, aka forks are. And if we do this, then we're going to get basically all of the indices that correspond to our iota sequence that's not equal to our positive numbers from our original list. And so we now have a very convenient function called where in APL that'll basically give us back the values in an iota sequence that correspond to our indices here. So we're expecting to get back 2, 3, 4, 5, 6, 7 here. And from here, all we need to do is take the first of these elements and we're good to go. So that is our full solution. And our final solution is only slightly different because we make this point free. And in order to do that, so here we basically have our first 3 train. And here is another 3 train. So this is 2 unary functions. And then we have a unary function and a unary function. So we have 4 unary functions here. So basically we want to, in order to get a B combinator, we have to turn these 4 unary functions into 2 unary functions. And the easiest way I believe to do this is just by composing these 3 with 2 B combinators. And then when you have 2 juxtaposed functions, you should just get the B combinator by default, because that is what 2 juxtaposed unary functions gives you. So if we go F and we try to apply this point-free F to this, we should get our answer. And what's really cool is if you hit F, actually I don't think I have this turned on correctly, but if I go boxing trains equals tree, and then if we type F, this is going to show you a tree visualization where each of the 3 tines, whenever you see sort of a fork here with 3 tines, that's the S prime combinator or a fork, and anytime you see one with only 2 tines, that's a 2 train or the B combinator. So I'm not going to go into detail about how to read this, but it's pretty awesome. So let's hop back now to our APL solution, modify it a bit, and then compare it to BQN, and then look at the C++ solution and the C++ CUDA solution. So here we are back looking at our more polished APL solution. Hopefully this makes a little bit more sense now that we've walked through it. Note that I believe one of the composition operators that we're using can be removed. But that's not a big deal. So let's try and, in an ideal world, make this a little bit more pretty. So as I mentioned, there's no sort primitive in dialog APL, and we also need to use the 2 symbol sort of tack atop in order to disambiguate between reduction and compress. But in an ideal APL, we would have a sort primitive, which in BQN they use as the logical AND. In the unary case, and we've also removed those 2 Unicode symbols, the 2 glyphs, to disambiguate because a reduction is a superscript in BQN, so there is no ambiguity there. And also too, we can actually move the sort now inside our parentheses and save ourselves 1 character, which is just code golfing, but it's the exact same thing. And if we compare this now to our BQN solution, you can see that it is very similar, basically identical up until the fact that BQN uses not equals instead of tally for the size or length of an array. And then it gets slightly different. You can see that our iota underbar in our APL solution doesn't exist in BQN. It does, the algorithm does, but it is the slash, which is called replicate instead of calling it where. Or actually, I think it's called indices. Replicate is something different, which we saw on the right. And our pick looks slightly different, and you can see a couple +1s as well. That is because APL by default is 1 indexed, whereas BQN is 0 indexed. And also you can see where we use iota for calculating a range or generating a range, we use the sort of up-down arrow for range. So BQN, pretty nice. Almost makes me wonder if BQN should have been 1 indexed as well, because I do sort of like the solution on top slightly better. But that is a discussion to be had with Marshall Lochbaum, the creator of BQN, at a later date and time. So now let's go on to our C++ solution, which is obviously going to look drastically different, but semantically is quite similar. So it's actually pretty concise for C++, that is, and we're making use of 3 algorithms: partition, sort, and mismatch. So basically our partition is doing something very similar to what we were doing by filtering out the evens and then doing a take with the length of sort of n+1, where n is the length of our list. A partition is based on the lambda that we're passing. It's basically going to sort our list such that all of the elements that pass our partition are going to be in the first or the front of our list, and then all of the elements that fail our lambda are at the back of the list. And so here we're doing not only just the negative elements, the ones that are less than 0, but also elements that are greater than n plus 1 are going to be the ones that are pushed to the back. So any element that's greater than 0 and less than or equal to n is going to be kept at the front of our array or vector. And that's basically the equivalent of what we did in APL, but a little bit simpler and sort of all-in-one algorithm. And once we have our vector partitioned, we basically just need to sort that first partition, which is why we're sorting from the beginning of our vector up until I. So the iterator that is passed or that is returned from partition is the iterator that corresponds to the start of the second partition. So all of the negative numbers and the numbers that are greater than n plus 1. So we only want to sort our first partition, and then once we have that, we're basically going to call an algorithm that in many cases is terribly named. But in this case, it's actually the exact name that we want, which is mismatch. And so we want to find the mismatch between the sorted elements in our first range, which we can just pass vec as our range because we know we're going to find our answer before we get to the second partition. And we're going to be comparing that with a list of numbers that increment by 1 and start at 1, which we can get very nicely because of C++20. We get that from our views iota. And note that std partition and std sort are C++, I think, 98 algorithms, but the std : ranges : mismatch, that is a C++20 algorithm. And the reason we're using that is so that we can pass a std views iota to this as one of the arguments. Note that the first two algorithms, partition and sort, take 2 iterators, but the mismatch algorithm takes 2 ranges or views, which is super awesome. And then once we've called mismatch, we basically just return what is in the second element that we found when we got a mismatch, which is going to correspond to the first missing positive, which very oddly they call the sort of 2 elements in1 and in2. So an in2 is going to be an iterator, which is why we need to dereference it. But once we've done that, we are good to go. And a couple of you that are C++ veterans might be thinking, how come I didn't use the C++20 std : ranges : partition algorithm? That's because if you do that, I don't really think it's a huge win. You can use the C++20 partition algorithm and save yourself passing in the 2 iterators, but then what you get back is a range. And so in order to use that range with our sort algorithm, which we definitely want to use the interface that takes 2 iterators, you then have to call std : ranges : begin on that range. So between the two, I don't really think it's a huge win by using the C++20 algorithm. This is the version that I think I kind of prefer, but honestly, it's not a huge preference. But if you were thinking that, that is where the difference comes from. So now let's transition from C++ to CUDA C++, which we are going to do by making use of thrust algorithms. So this is now compilable using NVCC if we get rid of the C++20 ranges algorithm. But for basically anything that doesn't use the C++20 stuff, you can just use the NVCC compiler. And how do we migrate this so we can run it on the GPU? Well, the first thing we need to do is change the std vector to a thrust device vector. That's pretty straightforward. Then we change the namespaces on all of our algorithms, partition, sort, and mismatch to be thrust partition, thrust sort, and thrust mismatch. These all exist in the thrust standard library because it was modeled after the C++ algorithms, standard algorithms. Note that we went from the C++20 mismatch back to the C++98 thrust mismatch. And on top of this, in order to get our lambda to work, we have to add the device attribute to our lambda, which is not too difficult. And then we have to make a couple small changes. So in order to get the thrust mismatch algorithm, right now we're passing 2 ranges, which doesn't work. So we need to change the vec, which is passed in as a range, to be 2 iterators again. So that's going to be vec.begin and vec.end. The views iota doesn't work with sort of MVCC yet, but we do actually have something that does this exact thing, and it's called a counting iterator, which exists also in the thrust standard library. So a thrust counting iterator, when you pass it the initial index of 1, is basically going to give you the exact same behavior as a std : views : iota. And once you've done this, the only thing you need to change is that because we're no longer using the C++20 mismatch algorithm, which returns you the .in1, .in2, the thrust mismatch, similar to the C++98 mismatch, just returns you a pair, which you get the second element of a pair by doing a .second. So that might have seemed like a lot of changes, but actually, if you compare these two to, if you compare the CUDA C++ to the original C++, It's very, very similar. Basically, you just changed the namespaces on the algorithms, upgraded your vectors to device vectors, annotated your lambdas with the device attribute, and then in certain cases, like when you have a views IOTA, you might need to reach for a different tool. But other than that, these are very, very similar. So I find this, in terms of transitioning from C++ to CUDA C++, the easiest way to get started. I will leave links in the description down below to all of the Thrust and NVIDIA CUDA documentation if you're interested. And I believe that's where I'm going to leave this video. So I hope you enjoyed. I hope you learned something. I know I covered a lot. If you have any questions, feel free to leave them down in the comment section below. Go check out Asher's video if you would like. I will leave a link to my recent online talk that I posted on this channel called Functional versus Array Programming. If you enjoyed this video, I encourage you to check out that video as it covers similar topics.